Well, hello there and welcome back to another video. So, lately I have been learning some things about parallelism and multi-threaded code in Rust. And in this video I would like to explore some of the modules that come in the Rust standard library for doing parallel multitasking, and also maybe compare those things to Rayon, which is a data parallelism library that is very nice. So yeah, that's the idea. By the way, I'm a total noob with this thing, so please don't take anything that I say here very seriously. I just maybe wanted to share some of the things that I learned, because I think that sometimes it's nice to put the things that you have just learned into words, and trying to explain them also makes it more effective learning experience, I think. And it may also be useful to hear about someone who's just learning about some stuff and seeing what problems may arise and that kind of things. So what we are going to do in this video is we are going to take a look at an existing program and trying to parallelize it so that it basically runs faster. It makes better use of the cores in the CPU and reduce the runtime, hopefully. So specifically, I want to look at different modules from the standard library. That would be the standard threads, which is just the API for dealing with threads without any, without anything more, like vanilla Rust threads. Also atomics, which are more like a lower level synchronization primitive to synchronize work with between threads. And also channels. These come in the multiple producer single consumer module. That is what they are called. And they are sort of a more higher level, let's say, synchronization primitive than atomics, at least. So we're going to do basically the same parallelization work for the existing program using these three different techniques, let's say, or different modules, and compare them, and also then compare them to Rayon. So let's grab this text and pass it to toilet to make sort of a video thumbnail. That font is not very nice, so let's use another font. I think there's one called SM Mono 12, which looks rather nice. Yeah, and you can even pass a kerning parameter to this program, which, as you can see, makes some of the spacing between the letters much better. This L and this E doesn't look as nice as this, which looks much more cozy. Let's clear the screen also, and maybe also let's use a small prompt. Okay, so this will be on one side, and let's do some poor person window tiling, and in this side write versus, because we are going to be comparing using the same font. So it's going to be versus Rayon. And for Rayon, let's use a bigger font. This Mono 12 is nice. And also let's add some color with lolcat. Look at that, that's really nice. Let's also clear the screen and use a minimal prompt. Yeah, look at that. I think that looks like a nice video thumbnail. Okay, so let's let's stop playing around with the terminal and jump into the code. So I'm going to be using a code example from Advent of Code 2022, which I finished actually like a couple of weeks ago, in like past the middle of 2023, but just a minor detail. And specifically, we're going to be looking at day 19, which is a very interesting puzzle And the details of the puzzle are probably not very important for the purpose of this video. Just so you know, there is a big function here called find max geodes, which is basically like the workhorse of this problem. This thing basically simulates, like runs a simulation over a given number of turns or minutes, and the more minutes you pass in, the longer it takes to compute the simulation, because it's basically computing all the possibilities of the simulation and then finding the one that maximizes a number of geodes, which is something that has to do with the puzzle itself, and then it returns that maximum number. And it also depends on an input called a blueprint, which is basically like a recipe for how you make robots and things like that for this particular simulation. But the details of this problem are not important here. Let's just treat this function as a black box that takes a blueprint and a number of minutes to simulate. The bigger this number of minutes is, the longer it will take to compute, and then it returns a number. So we don't need to dig into this function. We are not going to be parallelizing or anything inside of this function. We're just going to treat it as a black box. And this is basically the main function, the highest level one. So we can see what this thing does. It basically starts by parsing the input and generating a vector of blueprints. The input itself, it has this shape. It's a text file, and each line represents a blueprint. And there are 30 of them. So here in this vector, we're going to have 30 blueprints. And then the function does a couple of calculations, and in the end, it just returns a string with two numbers, which are basically the solutions to part 1 and part 2 of this puzzle. So if we run this with cargo run in release mode for day 19, well, it will compile and then run. Okay, so we can see that it printed these two numbers. These are basically the two solutions, the two answers. And it took, I'm also printing like how much time it took to run. It took about 800 milliseconds to run, so about 1 second. By the way, when I implemented this, I also found like a better, like a more optimized version for this find the max geodes function that reduces the runtime to much lower. It makes it much faster, and it takes just about like 15 milliseconds or something like that to run. But I disabled that I undid one of those optimizations for the purpose of this video. So in this last commit here, I just removed some early termination conditions that made basically the branching of this function, branch much less. And it improves performance. But if it runs in 15 milliseconds, I think I wouldn't care about optimizing this. But now it's taking like 1 second to run, so I would like to make it faster if possible. And let's pretend that I don't know any way of making this function itself faster. So we are left with basically the highest level stuff, and to optimize, and hopefully with some parallelization we can make this thing run faster on the whole. So let's take a better look at what this run function is doing. As we have mentioned, it is printing two different numbers, the solutions to answers to part 1 and part 2. And the answer to part 1, for instance, is just grabbing all the blueprints, iterating over them, and then computing this find max geodes, which is the important function here, with a parameter of 24 minutes or turns to compute, and this given blueprint, and it's also multiplying that by the blueprint ID. This is part of the description of the puzzle, and then it's computing all of those numbers and then adding all of those up. And part 2 is quite similar. It's just grabbing the blueprints, but it then only takes the first 3 blueprints, and for each of those 3, it again calls this find max yields, but this time with a higher number, with 32 minutes to compute, 32 turns, which is more expensive. And then it takes the product, it multiplies all of those numbers together. And that's it, basically, on the highest level. So looking at this, we can think of at least two different things to parallelize here. Like on a very high level, the most coarse-grained kind of parallelization we can do is, if you look closely, the answer to part 1 and part 2 are completely independent from each other. So this is not very common in advent of code problems. Many times, like, the answer to part 2 depends on the answer to part 1. But in this case, you can see that the code for part 2 doesn't reference this answer, so it's completely independent. And since these two things are completely independent, we could think of running those two things in parallel. And if how long it takes to compute both of them is comparable, then we might get a better runtime by running those two things in parallel. And also, you probably have noticed already that this is the expensive function, the find max yields, and we are calling this for each of the different blueprints, but each of those calls is basically independent from the others. So here we are calling this for each of the blueprints, so we are calling this 30 times, but these are basically 30 independent calls, and we could do that also in parallel, as well as these other 3 calls for the higher value of turns for part 2. We could also do these 3 things in parallel and then combine the results of them by multiplying them or by summing them together. So those are basically the 2 ideas that we are going to be trying out. Parallelizing 2 computations together, and then also parallelizing like in a loop. So okay, let's start by the more coarse-grained parallelization, like trying to run this thing and this thing in parallel. So before even starting with that, I think we should probably measure if it makes sense to do so. So let's do something. Let's grab part 1 and just hard code it to 0, so it doesn't take any time to run. And let's run this thing again to see how much time only running part 2 will take. So we can see that when only running part 2, it takes about half a second, like 500 milliseconds. So that's very promising. It means that almost half the time is spent on the part 2. And if that is right, then if we do the same thing the other way around and we disable part 2 and only run part 1, with this very ugly hack, we should see that part 1 also takes about half the time. And we can see that here it took 400 milliseconds to run only part 1. So that's very promising. It means that parallelizing these 2 together does make some sense. If it were the case that maybe part 1 only took like 1 or 2 milliseconds and then part 2 takes like hundreds of times more, then it wouldn't make much sense parallelizing those 2 things together, because the runtime of one would be like completely dwarfed by the runtime of the other. So, but in this case, it does make sense, which is nice. And let's try to do that then. I'm going to get rid of this, like go back to the initial version of this. And actually, before parallelizing this, I think I would like to refactor this a tiny bit by extracting these 2 computations to separate functions, just so that we have a very simple flow in this run function, and we can understand like this is just one function call like for part 1 and then one function call for part 2. So let's call this thing, well, the same thing as the variable, maybe total quality level. This name of total quality level is just a reference to the puzzle description, basically. the same thing as geodes and blueprints and all of that, which we don't really care about. We just care about parallelization right now. Let's also extract this and call this thing max geodes product. Okay, and this is part 2, so let's move it below part 1. We can get rid of these type declarations because now it can be inferred. And well, this extraction, I never liked that the extract function refactor doesn't know about, you know, not like it used vector instead of a slice for this parameter, but I think in general it's nicer to just treat these things as slices instead of receiving like references to vectors. So let's do that also. And well, I also want to be a bit generic and call this thing answer1, which by the way, this is a problem of Rust. I think Rust Analyzer, like the language server, that doesn't understand when renaming something. It doesn't do the renaming inside of macro calls, which is a pity. So this is answer2. Okay, but yeah, with that, the code should still be the same. Let's check that we're still getting the same answers. Indeed. And let's actually commit this to use it like as a base version for everything else. So let's do day 19, extract part 1 and 2 into separate function. Okay. So with that out of the way, we can now have, like, right now the run function is like much simpler than before. It's just 2 calls here and the formatting of these 2 answers. So how do we do this? How do we run these 2 things in parallel? Well, one way to do this would be to use a separate thread to run, like to spawn a new thread to run the part 1, then run part 2 in the current thread, and then wait for part 1 to be done. So to do that, we can use, there is a function in the thread module, if I can type correctly, thread spawn, this function, that just takes a closure and will run the code inside this closure in a different thread. So we can put this thing inside of here. And well, that should be it for spawning a thread. But we can see that there is a problem here because answer1 is no longer just an integer. It's now a join handle of an integer. So this is basically the thing that you have to call join to wait for the computation of this. So if you think about threads, it's like, okay, this computation is going to be done in another thread. Then you have to somehow get the result of that thread. And to do that, you can call join. And this join actually returns a result type, so you have to unwrap that result. Here we are not caring about doing proper error handling, so this will panic if the result was an error. And that basically happens if this code inside of this thread panics, then you will have the error of that panic in this in the result of this join. But we don't care about that, so we are just going to unwrap that. And by the way, if you know anything about multithreading, you already know that this won't work for making this thing in parallel, because we are just joining after spawning this thread. But let's not care about that. Let's first try to make this thing type check and compile. So we have another error here, and this is not very readable, so I'm going to see the error here in the console, which I find a bit more readable. And it says, closure may outlive the current function, but it borrows blueprints, which is owned by the current function. And that is a very descriptive error. And it also has a suggestion to use the move keyword here. So let's try to understand what's happening here. Actually, let's maybe even first get rid of this join and not care about like printing this answer 1. Let's just have this. You know, we are spawning a thread and we are not doing anything with this, and then we are computing part 2. So this still has the same problem as before. And why is this problem? This is a very interesting problem that Rust is telling us about. Like, it's an actual, you know, bug in our code, and a very serious one. And it's very nice that Rust catches this. Basically, think about what will happen here. Blueprints is a local variable inside of this run function, and it's a vector. So this is some memory, like a vector manages some memory on the heap. And when this function ends, well, this local variable will go out of scope, and it will be automatically clear up. There will be some compiled code that calls the drop function on the vector, and that will clear up all the memory, and we don't have to care about that. Like, Rust is very nice for providing automatic memory management without having to worry about, or without having the cost of a garbage collector. So when the run function ends, blueprints variable will get dropped, and all the memory associated with that will get cleared. But this function that we are passing to thread spawn, this is going to be running on another thread, and that may take longer than the current thread that is running the run function. So the current thread may, imagine that maybe answer 2 is like this call is faster than this thing, so it may end before this this other thread begins executing, or in the middle of its execution, and this other thread is accessing this blueprints function. So if this thing ends and clears that memory, this thing will be accessing invalid memory, which is a very serious bug, memory safety bug. Like, it's a use after free, and you could be reading garbage, you could be reading things from like another thread, anything could happen, have a segmentation fault, whatever. So it's nice that Rust can like tell us about this and actually prohibit us from even trying to run that, even having that thing happen. So we don't have to deal with those hard to catch bugs. So how do we fix this? Well, one of the suggestions from the error message was to use a move keyword here for this closure. And what move does is it makes the closure, this thing, take anything that it references from outside of its scope is going to take them by move. So basically, it's going to carry the value of the blueprints variable with it, and that value is going to be moved along with this closure, and then it's going to be passed to thread spawn. So basically the closure is going to take ownership of these blueprints, which actually gets rid of that error, as you can see. But we have another error here, which is a classic Rust error, which is use after move, borrow of moved value blueprints. So yes, we are trying to use the blueprints value after it has been moved in the previous line. So basically, when something is moved out of, this is basically this, has the same effect of this thing being out of scope. You cannot no longer use it after that, because now this thing owns it. So how do we get rid of that? Well, one possibility would be to have another, like a copy of this. So if I can type blueprints 2, let's say it's just blueprints clone. And well, in order to be able to clone this vector, we'll have to make, this is a vector of blueprints. Where is it? The type. So this is a vector of this struct type. We would need this thing to also be clonable. So let's derive clone. And with this, and using the second blueprints array here, this thing now compiles, or doesn't have any errors. And we could actually do join and unwrap here and have the answer 1, and this should work. So let's try this. Answer 1. And if we run now, well, it should run, but we are not going to be seeing any better performance. In fact, it took longer, but I guess this is just noise in the, it's just normal variance between runs. So it's still taking 800 milliseconds. Why is that? Well, because we are spawning a thread to do this calculation, but then we are immediately blocking the current thread to join this. So we are not doing anything useful in the current thread while this thing is running. We are just waiting for the answer, and then after getting that answer, we are running part 2. So basically, this is just spawning a thread to do sequential programming the same way as we were doing before, just more complicated. So in order to fix this, it's pretty simple. Basically, this is not the answer 1. This is the answer 1 handle, and we can do let answer 1 be this answer 1 handle, join and unwrap after we have computed answer 2 in the current thread. So now we are spawning a thread sorry, to compute answer 1, then compute the answer 2 in the current thread, and then waiting for the answer 1 thread to finish. And if we run this thing now, we should see a lower runtime. Yes, 500 milliseconds, almost half. And this is because, of course, like my computer can run multiple threads at the same time as any modern computer can. If I only had like one processor without hyperthreading or anything, this wouldn't make any difference either. But since I have multiple cores, this works. Okay, so that's it. That's the way of parallelizing 2 computations, but it's not very nice, right? There is something that really bugs me out about this, which is, do we really need to clone this blueprints vector? Like, wasn't one of the supposed benefits of Rust, having fearless concurrency, like being able to, this is not a mutable variable, so it should be safe to access this thing from different threads or from different places. Like, Rust should let us do this kind of thing, and indeed it can, but we have to do a little trick for that. Basically, the problem here is that we are just spawning the thread with this thread spawn function, and these kind of threads can only basically access static memory, so things that live for the whole duration of the program. Anything that is local to this function they cannot access unless they do this trick of moving things along with them, which sometimes might be a good idea, but let's try to not do that. So how can we make this thread access things in the current scope of this run function? Well, to do that, there is an aptly named function called thread scope, which basically gives you the ability to spawn scoped threads. This thing takes a closure as a function, and it will pass to this closure a scope parameter. Let's call it just S. So S is of type scope, and this scope thing allows you to do to spawn threads from it. So basically, you can call scope.spawn, and this is basically the same signature as thread spawn, but the threads, like this, will take a closure here. But the guarantee that thread scope gives us is that these threads will only live, will all be joined and weighted. They will all be done once the call to thread scope is done. So after this, in this line, all of the threads that were spawned before in here are going to already have been done and been joined. So that guarantees that these threads can access anything that is in scope in this function, because they cannot outlive this function. And that is really useful, and it's basically what we want to do here. We can actually move all of this computation inside of this closure. And then another thing about this is that it's this function is quite convenient in that it returns whatever the return value of this closure is. So here we are returning this formatted string, and this thing will return that, and it will make run return that. Okay, so here instead of using thread spawn, let's use scope spawn, and that's it. Now the error is gone. This thread can now access the local variable blueprints, and this other function can also access the same thing, so everything keeps working, and we didn't need to make a copy. So we can run now, and yeah, we also get the runtime improvement. So okay, that is basically one way of parallelizing two functions or the two tasks and running them together. Maybe you, if you're like me, you may not really like the asymmetry between these two calls. Like we were parallelizing this call and this call, and for one we are doing threads like spawn, and for the other we are not doing that. We could, for the sake of symmetry, we could also do like scope spawn here, and then we will have answer to handle, and then we can wait for those two things. But it's completely unnecessary also to do that. You will be spawning two threads and then just blocking the current thread, waiting for those two. So this is, I think, a pretty common pattern when you need to parallelize two things. It's like, okay, spawn one thing to be done in another thread, and then do the other thing, and then wait for the first part. So this is basically what we are doing here, and it's pretty similar to what you would do, for example, in Bash, when you can run something like, I don't know, something expensive, let's say, and you run it with ampersand at the end. It will run this thing on the background, and then you can wait for it. Although Bash is kind of a mess in that regard, because everything prints to the same terminal. Here in Rust things are a bit more better structured, I think, and you can think of threads as like single functions that will give you back a result, and you can then use that result. Like you can join them and use that result. So basically, threads compose in a very similar way to how functions compose, which is really useful. Okay, so we have done this coarse-grained parallelization that we wanted to do, and running part 1 and part 2 in parallel. Let's actually add these changes, not commit them, but add them, because we are going to use this to then do the finer level parallelization bit, like trying to parallelize each computation of this for each blueprint. We are going to do the same idea with threads, atomics, and channels, but we are going to keep this same approach of parallelizing the two parts together. So let's use this as our base code now, and let's think about, okay, we are now running part 1 and part 2 in parallel. Can we actually run in parallel each computation within part 1 and part 2? Like each of these calls to find max geos, can we run them in parallel? And indeed, we can. Let's first do it as we did with this thing, using just standard threads. So here, what should we do, for instance, for part 1? Well, we could, here when we are mapping, we could spawn a thread here. And by the way, I could try to do thread spawn, but we already know that since we are going to be reading from this blueprint variable here, and this is a local, like this blueprint variable is a reference that comes in this array or this slice, and it's local to this function. We know that in order to access that, we are going to need to use scope threads. Oh, by the way, I still have this derive cloned, which we don't need. Let's get rid of this and maybe have it back if we need it at some point. So let's also add that. Okay, since we know that we are going to access a local variable here, we are going to need scope threads. So let's start by doing thread scope here. And we are going to basically put everything inside of a thread scope. And well, here we can do scope spawn, a function, or a thread, sorry, to do this computation. And okay, if we are like spawning a thread to do this, then we are going to try to sum this thing together. But this thing doesn't return an integer, it will return a thread handle to join. And of course we could do join and unwrap here, which is basically what we first tried when we were doing this on the main function. But if we do this, you can probably already guess that this will do sequential computation. And in order to prove that, let's make part 2 do nothing, so it doesn't take any time to compute, and let's run with this. We have some warnings about unused things, but yeah, okay, we are having the same answer for part 1 still. Part 2 is just 0 because we commented it out, but it didn't get any faster. And why is that? Well, because this thing is basically running all of the computations sequentially. If you think about how iterators work in Rust, is like we're doing blueprints iterator, then wrapping that with a mapping iterator, and then adding all of those things up. But the map the map call is not eager. Like it won't call this this callback with each element until we call something on that iterator that makes it consume that iterator, which is the sum call. So it's only when calling sum that each element will be iterated, and for each iterated element we are going to be calling map. And so we're going to be calling map on the first item. This will spawn a thread and then join it and wait it. Then we're going to be calling that on the second one, and it's going to do the same and adding those things together with sum. So this is basically doing sequential computation. So what we would need to do would be to first spawn all the threads and then wait for them at the same time. So in order to do that, we can keep maybe this map but not call join and unwrap. And instead of doing the addition here, we can collect all of these handles. And we can collect this into another, like a local variable here. Let's call this thing handles, which would be a vector. Okay, and then we can use those handles to, we can weight them all. How can we do this? I guess we can iterate them, join them. Well, we need to call and wrap, and then these things we need to sum. And this is complaining, but moved due to this method call. Well, we're going to take a look at this error, but okay, so the idea here is we are calling collect, so this collect call is what is forcing the iteration of this iterator and calling this map. So this is what will trigger all the threads to be spawned. And then once all of the threads were spawned, we can wait for them or join them and then add all of those together. So let's take a look at that error. Cannot move out of H, which is behind a shared reference. Yes, this is because, yeah, this is very interesting also. So the join function on the join handle on these things, which are called, well, join handle or scoped join handle. This thing, this join, consumes that. Like you can see, it takes self as move reference. So it will consume the handle itself. This is done so that it guarantees that you call join only once. Because basically, think about what happens when with the memory of whatever gets returned from this closure. In this case, it's just an integer, so it's not dynamic memory, but this will also work for anything that can be moved, a vector, a string, whatever. So when you spawn a thread, that thread will run, and it will give you back a join handle. This is a vector of join handles. And that join handle basically has the responsibility of taking ownership of whatever that thread returns. And when you call join on that, it gives you ownership of that thing that the thread had returned, and it basically dies out with it, so that the handle no longer exists. So it will not no longer own whatever was returned from that thread, and now you own it. You own it after calling join. So basically, here the problem is that we have this vector of these handles, and this vector owns these handles. So we have like a dual ownership problem here. We will need to either clone. I don't know if these handles are clonable. Probably not. Cannot move out of chart. Yeah, okay. Scope join handle doesn't implement copy. Okay, so it cannot be cloned, I think. But the solution here is basically, when iterating over the vector, we have to also consume the vector. And in order to do that, we can call into iter instead of iter, which will consume the vector itself. This is an iteration that you are basically saying, on this iteration, I'm going to take ownership of whatever was inside of you. And so you no longer have to handle that memory. And so then the vector dies. Like after this into iter call, you can no longer call, for example, if I wanted to do handles, I don't know, length. Well, this probably needs to be coerced. Like, let's say that the answer now is the handles length. Let's make this thing compile. What's your problem here? It doesn't know how to sum. I just want to showcase something stupid here. Okay. Now it compiles, and then it is complaining about this what I wanted to show, like is using handles after it has been moved, because this into iter is consuming the handles. So we can get rid of this. We can still return this sum, and that's it. Yeah, so now we are consuming these handles with into iter, and then each handle we are consuming it with the join. So we are getting the results of each thread, and then we are adding all of those up. And that's it. This should now be running every blueprint, find, max, geodes calculation in parallel. So let's run it now. This is only running part 1 because part 2 is hard-coded to 0. And yeah, look at that. Now the runtime went down to like 100 and something milliseconds, like less than 150. That's really nice. And well, we knew that in the original input there were 30 blueprints, and this didn't decrease the runtime to like 500 milliseconds divided by 30. And this is because each blueprint has some of the blueprints take much longer to run than others. So probably there is one blueprint that is taking like 100 milliseconds or something to run. I have already taken a look at this before. So yeah, there are some that take longer to run. But anyway, we decreased the runtime of part 1, and now if we enable part 2, we will still see that the thing will take half a second to run, because part 2 is still taking half a second. And indeed. But we can do the same kind of parallel work that we did for part 1 on part 2. So we can maybe even copy this code and adapt it. So part 2 is basically doing something very similar, but instead of iterating over everything, it's iterating over the first 3 blueprints. Then instead of doing this ID times this, it's just doing find max geodes with 32 minutes. So let's use this instead. Yeah. Then we can collect all of those numbers, and instead of doing the sum, we can do the products. And that's it. That should be part 2 parallelized the same way as part 1. And if we run now, we get 300 milliseconds or 300 and something. And we are not going to get any lower than this because I have already checked, and one of those 3 first blueprints takes around that time to run for 32 turns. So, you know, without getting in, like inside this find max geodes function, we cannot make this run any faster. But it is already quite a significant improvement over what we had at the beginning. And we're also making much better use of our CPU basically here. For example, for part 1, if we had like a file with, I don't know, double the amount of entries of blueprints, it would have taken like double the time to execute. But now, since we are parallelizing things, well, it will take also double the time, but since it's double the processing time, but since it's doing things in parallel, it may take, you know, less than double than it were all sequentially. So, okay. That is basically how we could approach parallelizing things just using the standard thread. So let's maybe have a copy of this, because I want to, in the end, maybe compare and contrast the different solutions. So let's call this thing not enough minerals threads. Okay. And let's go back here to what we had before. Before parallelizing part 1 and part 2, like inside of part 1 and part 2. And think of maybe another alternative of how to do this. So when parallelizing using threads, let's actually take a look at this. We had to do this intermediate copy, or intermediate, not copy, but intermediate allocation of the handles to know which threads we had spawned, and then wait for these things. So is there any way that we could get rid of that? Well, one idea could be to basically have, you know, spawn threads for each of these computations, but have all of those threads accumulate the result into a single variable. So this is basically a more imperative approach to this same solution, which we could actually do here using a classic for loop. So we can, you know, instead of doing this with iterators and doing iteration, map, and then sum, which is really nice, we could do also a for loop over this blueprint. So let's say for blueprint in blueprints, I'm going to yank this out. So for each of these, we can just accumulate on this sum variable, and in the end, just return this. So yeah, this is basically the same code as before, but written in a more imperative fashion. And it should still give us the same answer, which it does. This is the answer to part 1, and it's always been the same. So okay, with this, we can now think of another alternative, which is, okay, we are doing this loop here, but what if we, instead of calculating this in the current thread, we just spawn a thread that does this accumulation inside the thread, and that's it. Well, let's try to do that. Again, we are going to need the thread scope, because these things need to access local variables. So we can use a scope here, scope threads. We can do the loop as this, and we can do, okay, scope spawn, and move this increment inside of the thread. And basically also this thread scope is guaranteeing us that all of these threads that we have spawned here will have finished by the time we are accessing this sum here. So will this work? You probably are already guessing that this won't work. And this is because we are sharing a mutable variable between different threads. And that's something that's, one of the basic memory safety guarantees about Rust is that mutable is not really about mutability mostly. It's about exclusive access. So here, you can read mute usually as exclusive. So we have an exclusive reference to this sum, and then we are just spawning different threads and different things wanting to access this. So Rust won't allow that. So if we see the error message, well, actually mix match types. This is why is it expecting this? I'm not sure why. Okay, it was expecting something to return from the for loop, but that's not the error that I was caring about. Yeah, here it says cannot borrow sum as mutable more than once at a time. So very clear error message. Since we are spawning different threads, it would need to be like a shared mutable reference, and that's not allowed in Rust. So how can we fix this? Well, we would need some sort of integer value that could be shared between threads, and that's exactly what atomics are. We can use an atomic U32, and this will import them. And I think there is a new function here. Yes, we can have it initialized as 0, and we don't need this thing to be mutable actually, because it's not about mutability. It's about like shareability or exclusivity. And these atomic things can be shared between threads, but okay, they have a different API than normal numbers, so they cannot be incremented like this. Let's actually maybe call this thing, what is it called? Quality level, I think. Again, this name has to do with the puzzle description. Here we are computing the total quality level by adding up all of the quality levels that are computed like this. Okay, so we have the quality level, and we want to add this to the sum integer. And for that, there is a fetch add function that will take the value that we want to add, in this case is quality level, and an ordering parameter. And this ordering parameter is, well, a bit I don't want to say confusing, but it's a bit like advanced, let's say, and I'm not going to pretend that I understand all of the ramifications of the different orderings, but I'm pretty sure that here we can use relaxed ordering for this. Import ordering from this atomic ordering. And then we cannot just return this because this is an atomic U32. We need to read from this using the load function. And again, this takes an ordering. So let's use ordering relaxed, which I think should be fine for this example. So ordering basically is a parameter for these atomic operations. By the way, I didn't even explain what atomic means. This is basically a type that allows you to do atomic operations on an integer. And atomic operations basically mean, for instance, here we are adding to it. It means we cannot have this problem of, for example, you have two different threads, and if you have like a plus equal operation, and that's like in machine code means, okay, load the current value of this, add it, and then write it to memory, and it might be like 3 different instructions, although it probably isn't in modern architectures. But if more than one thread can, they are interleaving together, and they can both read the first value and then one increments it, but then the second thread had already read the first value, then computes the addition and overrides the value of the first thread has written, that's a typical like race condition or like non-atomic operation problem. And that is a classic thing that can happen when you have multiple threads. And in this case, these atomic types allows us to not have to deal with that. Whenever you call this fetch add, it's going to do a fetch to read the current value and add to it, but all atomically. So it cannot be lost or overridden. If two different threads try to do that at the same time, it will be like two atomic additions. It will be the same as them doing it sequentially, basically. So that's what this atomics allows us. And then all of the operations on these atomics receive this ordering parameter, which basically this ordering, I won't try to explain it very thoroughly because I think I will do a very poor job at that. But this basically is a guarantee about, or not a guarantee, but it tells Rust and the compiler what things can be reordered, like which instructions can be reordered before or after this operation. So when you're saying like relax, because the compilers and even CPUs like to reorder things and execute things out of order if they think that they will get the same result. But when you have multiple threads running together, those guarantees might not might not be the same as when you're running single-threaded. So when you say relaxed, it basically will keep being atomic, this addition, but it has no guarantee about whatever has run, instructions have run before or after it. And in this case, I don't care about that because each thread is just basically computing one thing and then adding to this and not reading again from this variable or anything. And then all of the threads are getting joined before executing this load. So I think this is safe to do. If you're not sure about this, there are other two like more strict orderings. One is release acquire, or acquire release, which is basically the kind of ordering that you have when using like locks or mutexes. When you say, okay, an operation is done with acquire ordering, it means that, well, anything that has how is the acquire and release? Yeah, nothing that has executed before can be reordered to be executed after. And these orders only make sense to think about them if you're having multiple operations on this sum. So if at the beginning of here we would have loaded, have done like some load and read this value to do something, and then that value would have been used for this addition here. Okay, you really want to have that load happen before this addition, and the addition to have to see the actual value of that load. That's probably not the best explanation. So anyway, these things are not the most trivial things to think about, and that's maybe one of the reasons why I don't really like using atomics for this. But anyway, I just got very lost in that trying to explain ordering, and I think I totally failed at that. But if I didn't make any mistakes here, we should have part 1 now running in parallel. Let's also comment out part 2 to run this. And yes, we are getting the same kind of speed up that we had before. And well, we are doing this accumulation of things using a single atomic integer. So we are not having to do this intermediate accumulation of values to get all the thread handles and those kind of things. So this could be nicer for some purposes, but I personally feel it's a bit awkward, and having to think about even writing down this orderings is I don't know, I find it a bit verbose and, you know, cumbersome. But okay, let's try to follow along and do the same kind of thing for part 2, which we will get into a different problem here. So let's again copy paste code, and here instead of computing a sum, we are computing a product. So well, if I can type product, so we'll need to initialize this as 1 to multiply things over here. We don't want to iterate over everything, we have to iterate over the first 3, and then we are not computing this quality level. What we are computing is just this, which we can call, I guess, max geodes. Okay, and instead of adding, we need to multiply. But we can see that there is no multiply method here. We have fetch add, and max, whatever. And this has to do basically with what has to do with which operations CPU architectures can actually do atomically or have any guarantee about doing atomically. So multiplication, as I understand, may take multiple CPU cycles to do. So therefore, there is no atomic multiplication to do here. But we have a very generic fetch update function, which let us pass in like a generic function to execute here. So what does this take? Okay, it takes 2 orderings, and we will have to explain that, I guess. Well, let's actually use the hardest ordering possible is this sequentially consistent order, which is abbreviated to this horrible name, seqst. And then this thing takes a function that will receive the current value and lets you you know, compute what you want this value to be updated to. So this is a U32, and here we want to do, okay, this value times max geodes, because we want to do a multiplication. What's the problem here? Okay, it's expecting an option because, yeah, this thing well, expects an option. Why does it expect an option? Well, because if you what's the problem here? Unused results. Yes, I guess this thing can fail. And this basically is no magic, since there is no, you know, you can do any computation here, and there is no atomic multiplication to be done. What this thing will do is basically do a busy wait in case, you know, it will read the value that it had before, this product atomic had before, do this operation, and then there is an atomic operation that is called like compare and swap. So it's going to compare with the previous value, and if it hadn't changed it, it will swap it with the result of this. And if it had been changed by another thread, then it will know that, you know, something has altered that value, and I think it will busy wait trying to update it. I'm not actually sure about that. And applies the function so that it returns. Yes, the optional result has to do with whether you are returning some or none here, so it will propagate this for you to know about that. And this is because you may not want to retry writing to this so many times. You know, if you have a lot of contentions with many threads trying to write to the same thing, you may want to, I don't know, try a couple of times and then fail and say, okay, none, and then you can return none here and know if this function has returned none. But in this case, we are only adding this thing or multiplying this thing 3 times, so it doesn't even makes sense to care about the ordering, you know, or if this thing is expensive to do in the hardest ordering, because it's just a couple of multiplications. So let's not think about that. Let's run this. And hopefully, yes, we have the same kind of runtime that we had before. So this is basically the same logic that we had done with threads, but now using atomics, which is more lower level, and you can probably tell that is kind of lower level. We have to care about more, I don't know, processor related stuff. And yeah, you can also probably tell that I'm not the hugest fan of this approach, at least not for this problem. I think it's kind of an overkill to go for atomics here. So let's rename this to, no, not rename, let's make a copy and call this thing atomics. And so, okay, let's revert now these changes again. And finally, let's try to, well, not finally, because we have to still take a look at Rayon, which will make everything much better. But before going to Rayon, let's try once again, but this time using another synchronization mechanism that is not as low level as atomics. And these are channels. So yeah, let's just go for it and see what happens. So channels, this come in the, as I said, multi-producer single consumer module, and this module has a channel function. This channel gives you back a tuple with two parts, a sender part and a receiver part. Okay, and basically you can use the sender to, you know, have multiple, this is why it's called multiple producer, single consumer, multiple threads, multiple consumers sending things to this channel, and then a single thread, a single receiver reading from that channel. So that's, you know, that maps quite well with what we want here. We want to have multiple threads running this, producing different values, and then receiving all of those and summing them up together. So that maps really, really well. Let's again use scoped threads here. So we're gonna have a scope. We can move this here. And actually this will kind of look similar to the atomics thing in that I want to use like a good old for loop. So let's actually copy paste that for part one. So here I think this is complaining because it doesn't know the type of this channel. The channels are typed, and they, you know, they are typed on what is being sent through these channels. But I think once we use the channel, it will infer the correct types. So okay, for each blueprint, we are going to spawn a thread. We are going to compute the quality level. Okay, but instead of adding this to this sum variable, we are going to send it to the channel using the sender. So sender has a send method, and we're just going to send the quality level here. And I think this will return a result. So yeah, we're going to talk about why this is a result and how this can fail, but maybe later. So yeah, this is complaining probably about not returning the correct type. Okay. I think we can probably inline this. Yeah, it's not so bad. And we then, well, we are spawning all of these threads here in this for loop. This thread scope also guarantees that all of those threads are going to have finished after this. And now we have to receive all the messages that those threads have sent into the channel. So, well, we are going to receive as many messages as blueprints there are. So we can do maybe something like blueprints, iter, map, and we don't care about the blueprint itself. We can do just receiver, receive, and this is again a result, so we have to unwrap it. So we are using just the blueprints to know the size. We could also do, I guess, in a more readable way, just from 0 to blueprint's length. Yeah, I think this is probably more readable. We're going to do the same. We don't care about the blueprints here. And we don't even care about these indices. We're just iterating 30 times, or the amount of blueprints there are. We want to receive all of this and then sum these together. Okay, and this compiles without problems. Let's again get rid of comment part 2 out. And if we run this, we have the same answer as before for part 1, and we have the number of running this in parallel. So okay, this worked. Actually, I wasn't expecting this to be as easy. We didn't have any problems with running this. By the way, I'm using here Rust, the beta channel, because I wanted to have something, you know, here the sender can be used directly from within all threads. But in the stable channel, you have to make a copy of this sender. So you have to do something like let sender clone and make this thing take ownership of that sender. This also works, but it's no longer needed in Rust beta. So this will also be available in the next release of Rust. So I don't care about using this, you know, non-stable feature for now, because it's just a change that is going to be released soon. But anyway, one thing that I don't particularly like about this code is this very manual iteration over the receiver here. So can't we do better? Yes, actually receiver, you know, since it has this receive method, it also has an iterator method. So receiver we can call iter, and this will iterate over all the messages that are sent to it, and you know, basically that. And we can iterate over this and just call sum, which is much nicer. But if we run this, actually, we are going to find that this thing hangs up and doesn't finish running. And this is quite interesting. Basically what's happening here is that the receiver is blocking, waiting for more messages, because it doesn't know that the sender, you know, if the sender can send any more messages, because the sender is basically still alive, and you know, different threads or someone could send things to this sender. So this is basically because the channels are, you know, basically you can think of a channel, a pipe or whatever, and it has two ends, a sender end and a receiver end. And in order for the receiver to know when no more messages are going to be received, the sender has to like hang up, like it's a communication, a phone communication or something. And once one of the sides hangs up, the other side can know that, you know, no more messages will arrive, in this case the receiver, or also the receiver can hang up. And if the receiver hangs up, then the sender send calls will fail and it will give us an error. I think this is an error, right? Yeah, send error. So that's why this sender send gives us back a result, because the receiver could have terminated. You know, maybe the receiver says, okay, I just was waiting for 3 things. I have received all these 3 things. That's it. I'm out. And then it no longer makes sense for the senders to keep producing messages, so they can know that, you know, the receiver has hung up and they no longer need to, they can stop processing or generating messages. But in this case, we would need to have the sender hang up before, you know, for the receiver to know when it can stop iteration, basically, and not stop receiving messages. And for that, we can just use drop of the sender. If we do this, the sender will hang up and the receiver will know that it has received all the messages that it had. And that's it. That also works. And before we didn't need to do that because we were executing receive exactly 30 times, or the amount of times of blueprints there are. And after that, we were no longer, like if we had called receive one more time, that last call to receive would have blocked because, you know, there was no message. There was no 31st message to be received. So we can do this, you know, hang up the sender and this works. Or we could also do, we can iterate and just take 30, or basically blueprints length messages, and you know, now the iterator will stop iteration or stop producing messages, and it will stop calling receive. Basically, this iterator is just an iterator that calls receive until receives, you know, returns nothing, which means that the senders have hung up. So if we only are expecting 30 messages, or the blueprint's length of messages, this should also work, I think. And indeed it does. And I personally find this a bit more readable than maybe doing that drop of the sender. So yeah, this is basically, again, another approach of doing this parallelization, but this time using channels. And we can copy this approach into the part 2. This will be, I think, very mechanical, or pretty much the same. So again, here we need the iteration to take the first 3. We are only iterating over those. We are then going to send these instead of these to the channel. Then we are going to take only 3, actually. And instead of summing them together, we are going to take the product. And that's it. I think if we execute this now, yes, we have the same answers as before. I already know these 2 numbers. And yeah, we have the same speed up as we had in the previous attempts. So this is just another way, and this is how channels can be used for the same purpose of parallelizing this. Instead of, basically, what I like about channels in comparison to atomics is that we don't need to think about ordering or any of that. We know that sending to the channel, you know, we can think much more in terms of like messages. But this actually, you know, if you think about this in comparison to, like, if in comparison to the atomics side, the atomics doesn't need any intermediate data structure or anything. But here we're using this channel, which internally, you know, this channel could have needs some sort of buffer or something to allocate and have all these messages that all of these threads have sent, because we are sending all of those without receiving, before receiving them. We could actually use a different thread for receiving these things, but I think it's, you know, not necessary at all, because the computation that is done with the results is just adding up 30 numbers, so it's like a very trivial thing to do. It doesn't need to be done in a separate thread, but we could do that. Like, first maybe spawn a different thread here that will receive things and add them up, and then at the end join that thread and return whatever that thread had. So in that case, you know, the internal buffer of the channel would probably not grow so long. We could do that if we had like thousands or millions of blueprints. That would be a different problem there, because if we had that case, the channel will grow a lot if we did this. So it would be better to have like another concurrent thread that would be consuming things from the channel while things are being produced. But in this case, we can do this. Anyway, let's again copy and paste this and call it channels. And okay, now finally we can take a look at what Rayon offers. So let's discard these changes, and actually also discard the first changes of the coarse-grained parallelization for running part 1 and part 2 in parallel. So I'm going to get rid of this. I don't want to screw up now. No, delete file. No, I don't want to delete. Which one is modified? This one is modified. Yes. Discard these changes. Okay. Now we have the 3 different versions using 3 different modules from the standard library. Let's compare these things to doing the same thing, or the same kind of parallelization work, but with Rayon. So in order to do that, we need to add Rayon as a dependency. So cargo add Rayon, and it took almost no time because again I have already tried this out. Okay, so first things first, how do we make these 2 things run in parallel? Well, Rayon has a perfect function to do that, which is called Rayon join. And this is basically the kind of low-level operation, the most basic operation for Rayon. This basically takes 2 closures and executes them possibly in parallel, but not, it doesn't guarantee that it's going to be in parallel. It just takes 2 things and tries to, run them concurrently or in parallel. So here, basically, we're going to have one closure that does this, and another closure that does this. And this join thing will return a tuple with those 2 things. So this is basically going to be a tuple with answer 1 and answer 2. And that's it. That's all there is to it. For parallelizing something with like 2 tasks with Rayon, it's very, very easy. Just there is a top-level function that does exactly that. And if we run this thing now in release mode, well, it may take a bit longer to compile. But yeah, we can see that the time has been reduced to half of a second, and we are getting the 2 answers that we were expecting. And we didn't have to care about like local variables or anything, because these things, Rayon guarantees that these 2 operations will have already been done by the time this join returns. So internally, these closures can refer to anything that is outside, like it's in scope. So it's awesome. And by the way, Rayon, what I mentioned about it doesn't guarantee that these 2 things will run in parallel, because basically Rayon, what it does, it's a thread pool library. You have a pool of threads to work on tasks, and each of these 2 is a task to be executed on that thread pool. So what will happen internally is that, okay, this first operation will be put on the thread pool for other threads to execute it, and the second one will be executed by the first, the current thread, as we were doing manually. And then after executing the second one, if the first one hasn't been executed by another thread yet, it will try to execute it itself, or it will take work from the thread pool to execute. So this basically means that if I'm actually going to be using Rayon for everything, or for parallelizing part 1 and part 2 internally, this makes a much better use of the CPU, because the thread pool is constructed to use as many cores as there is on my computer. But when we were doing in these previous solutions, we were executing or spawning new threads for each blueprint, and there are 30 blueprints here, and I think my computer doesn't have 30 cores to run, or I think it probably has 8 or 16 or something like that, or even less. So we were spawning more threads that can actually be run in parallel in my computer, but Rayon can be more efficient in that regard. It can, and if we had like more blueprints, we would have, I don't know, if I had like a million or 1,000 blueprints here, I would be spawning 1,000 threads, which would not scale up very nicely. But with Rayon, that can scale up very nicely, because it's not actually spawning threads for that. It's using the same thread pool, and threads are taking tasks to execute from that thread pool. So okay, this is the coarse-grained parallelization, but this is not the best part about Rayon. Actually, the best part is parallel iterators, and that is exactly what we want here for part 1 and part 2. So if we think about what we have been trying out with using threads or atomics or channels, it's basically the same pattern that we have. We have an iterator and a computation that is done for each element in that iteration, and we want to parallelize that computation and then do something with those results. So wouldn't it be nice if we had like a pattern that would be like an iterator, but a parallel version of that? Well, that is exactly what Rayon provides, and it's called, instead of iter, just parallel iterator. And we can import this from Rayon, and it has imported this prelude blah blah. I think the intended use of this is just import everything from Rayon's prelude, and you can then call, instead of just calling iter, you just call par iter, and that's it. Now this thing is a parallel iterator, and it will execute each of these functions, like map functions, in parallel, and then it will add everything together, and we don't have to care about anything else. We don't have to care about scoping and I don't know, nothing. Like, it just does the thing for us, and we can do the same thing on part 2, because it's basically the same thing. We can use a parallel iterator, take 3 of these, do this computation, and take the product, and it will just work. And if we execute this, we will get basically the same speed up as before, but the code changes were just, so much easier to reason about, because this provides exactly what we need, like a parallel iterator. We were doing, very manual things with threads and adding things into atomic variables and whatever. But if we had this powerful abstraction of a parallel iterator, we can just think, the same way we think with iterators, but underneath they are parallel, and I don't know, it feels so nice to be able to do this. So okay, that's basically it. That's 4 different solutions to the same parallelization problem. We can probably compare and contrast some of these. Well, first let's maybe take a look at the threads ones and compare it with, actually we can maybe call this thing Rayon, just to have a copy of each, and the base file. So let's discard the changes on the base file. Yes. And okay, now we have all of the versions, the base and the 4 parallel things. So if we compare, for example, the threads and the base, we can do compare selected. Okay, so here on the right we have the original version, and on the left the threaded using standard threads. Maybe this is a bit noisy to compare it like this. Yeah, I don't like that. Let's maybe do a split here. We have the threads over on the right, and let's have the base version on the left. So okay, we have this very manual way of spawning a different thread, but inside of the part 1 and part 2, like the pattern of using scoped threads and then mapping to this computation and spawning a different thread, like I don't think this is very complicated. And actually between the threaded, like using standard threads, atomics, and channels, I think I would I would go with simple threads solutions for this problem at least, because it's pretty similar to what we were doing originally. We are mapping, but we are just splitting the mapping part and collecting those thread handles, and then waiting for those threads to finish and summing those things up. We're splitting basically this computation into first do the mapping in different threads and then summing them together. But overall, I think it is a bit of a boilerplate to do all the thread scope and blah blah. But other than that, it's not too complex, I think. We can compare this also with the atomics solution. So I think atomics are not a great match for this problem. They are very manual and very low level. Like if you compare the code here with what was originally on the left, it's I think much more complicated to read. We have to care about this ordering things, and I don't know. I just don't like this thing, and it's unnecessary. Like it seems like unnecessary complexity for this problem in particular. But in some other problems, it might make sense to use atomics. Like if we have like a globalish kind of counter or something, and different threads that want to increment that or touch that thing, and some other threads that want to read that, it might make sense to use atomics for that. But in this case, it doesn't make sense because we don't have that case of having some threads read and some threads write on this atomic value. This is just being used as a local value, and all of the threads are just writing to it, and then the original thread is reading the final value from it. So, this is kind of a different pattern. It doesn't make sense to use atomics for this. And in a similar fashion, I think using channels is not very justified for this case if we compare this on the right to the original code on the left. So I do prefer this over the atomic solution because we don't have to think about atomic ordering or reordering of instructions in the CPU or things like that. Like this is a bit higher level, and we can just think about messages between threads shared in a single channel, which is nice. But again, like even comparing this with the in this side, let's say with the threaded solution, I think the threaded solution, manual thread solution, is more readable than the or less complex than the channel one, because again, this is like we are using channels for this thing, and I think the API of threads actually that you have, the threads, the handles of each thread keep the result of each thread is quite nice for what we want to do here, because channels and maybe atomics too are meant for when you have threads, long-lived threads that send things and they want to sync up with other threads during their execution. But in this case, we don't want that. We just need to execute something in a different thread and keep the result. And we don't care about communicating with that thread during its execution. And that thread doesn't care about communicating anything with us during its execution. So having channels is like, again, kind of an overkill for this. We can just use threads and it works. So between those three, I would actually go with using just threads from the standard library. But if we compare that to Rayon, well, we can maybe split again and here have the Rayon solution. Rayon is just so much less code. Like this pattern of spawning a different thread to execute two things in parallel is so much nicely expressed in Rayon with Rayon join. I actually think it would be really nice to have like a similar function in Rust standard library that just does the same thing as Rayon does, but encapsulate this kind of pattern of, hey, I have two operations. I want to run these two things in parallel and do that using standard threads. Not a thread pool, but it would be nice to at least have this or something like this in the standard library. But the thing that Rayon shines on is parallel iterators, which are just so much nicer than doing this manual parallelization that we were doing before. In fact, if we look at the git diff, well, we cannot look at the git diff because I have a new file here, but if we compare this, well, yes, we can compare the original with the Rayon one. So compare selected here. We can see that the differences, in this is just changing from iterator to parallel iterator, and that's it. That is the only difference needed to parallelize this computation. That is great. And in here, instead of calling these two things in separate lines, we just call them inside of this, pass them as two lambdas or two closures to this join, and that's it. We have parallel execution of those two things. So yeah, I think Rayon really shows what a nice API for parallelization can be. And it's a much nicer fit for this problem. So, okay, I think that's basically what I wanted to explore and show in this video. I did prepare sort of a recap for this, and I have it stashed. If we see, big stash. Yeah, I have this recap here. So if we do this stash pop, we can take a look at this file. Well, not the difference, but just the file itself. I did write this down to not forget about some things. So just doing a recap of the whole video. So about on the overall, there is this claim of Rust providing fearless concurrency, and I think this is very well grounded actually. It sounds like a marketing phrase, but as I said at the beginning, I'm quite a noob at threading and multi-threading and parallelization in Rust, but I had done some multi-threading work on other languages like C++, and in comparison, Rust feels so much nicer. Already the API of std thread is so much nicer, but also all the guarantee, memory safety guarantees that Rust provides. This thing about being fearless is really nice because it's actually, I think, very correct. Because okay, the compiler will tell you, about a lot of problems. You may stumble upon these problems while you're trying to do something, but all of these problems actually are very well founded. Okay, if I didn't pay attention to this problem, this would have been a memory safety issue, or a use after free, a race condition, all of these things. And Rust really provides very good safety guarantees for not falling into those concurrency traps, and that's great. I cannot express really how great that is if you come from another language. And I hope maybe in this video you saw me stumble upon some of those problems and I don't know, maybe reach a similar conclusion to me in this regard. Also, the standard library, the primitives that come in the standard library are really nicely designed and they play well together. So we saw that actually for all the solutions using the standard library, using threads, atomics, and channels, we were always using threads, and the atomics and the channels are very well designed to be used with the threads and just seamlessly work together. And that's also really nice. It really shows that there is a lot of great care put into designing these APIs. What else? Then about each solution in particular. So I have pluses or minuses depending on whether I think this is a pro or a con. About standard threads, okay. First of all, they feel like a very nice and solid building block for building other concurrency things on top of it. Like, I think the standard library, for example, doesn't come with a thread pool, or like, yeah, Rayon provides that, but it's not in the standard library. But you know, the basic API of the STD thread is already quite nice for building anything of that sort. I don't know, a multi-threaded web server, or a multi-threaded, I don't know, game engine, or whatever you want. Like, it feels like it's very solid to work with, and also it's very practical. Like, it's not just okay, powerful, but impractical. It's actually quite practical. I really like that this detail about the thread, the handles, not handlers, handles, keeping the result of the thread. So this basically makes the threads work as like functions, and you can think of threads as functions that execute in parallel, and that's great having that. And also the existence of thread scope function to being able to access things, local variables in separate threads, you know, in a safe way. That's really powerful, I think. And you know, in other languages you may have to really do manual work for that, like being sure that you know, you are not letting those other threads leave more than the current scope, because otherwise everything goes everything will explode, or worse, maybe you're reading garbage, or you may have, or maybe the worst case would be that, you know, everything works correctly, seemingly correctly, but you have some race condition that every once in a while things don't work, and it's a mess to debug. Like, debugging multi-threaded code is horrible. So it's really nice that Rust provides these safety guarantees and a practical API to build upon. On the con side, these standard threads are a bit boilerplate-ish, I would say. For doing simple things, like simple tasks, like the thing that we wanted to do of executing these two things together in parallel, they are not very succinct to express those this kind of simple tasks, and I think they could be if they had some utility functions over it. And yeah, they are also very manual. There is no thread pool or something, you know, higher level patterns like parallel iterators on the standard library, which I think, you know, I actually don't know if I would like to have those kinds of things in the standard library. Maybe they seem very useful, but you know, there's also value on having those as external libraries that you can easily import and use, because you know, the standard library is nice that it's well designed and robust, and if you do something badly on the standard library, like not very well designed, then you live with that forever. And we all know about languages that have things on the standard library that, you know, everyone agrees that they are trash and they shouldn't be there, or they were designed some, you know, decades ago, and now they are not good fit for modern code, but they still have to be maintained. So maybe it is good that things like Rayon exist as separate libraries and not in the standard library. Sorry, I have been talking too much already. I don't know how long this video will be, but I'm feeling like I'm starting to mumble more than usual. So okay, about atomics. It's nice that they provide a way of doing things and synchronizing thread with minimal overhead. Like, you don't need, you usually won't need to do extra allocations and things like that, like intermediate things to keep intermediate values, like we needed to do with threads. And they might be useful for other scenarios, not the one that we seen in this video, but if you need some sort of like shared global state or global-ish state that different things need to read and write at the same time. But well, they are very low level primitive, I would say, and the ordering rules are, well, here I wrote hard to reason about. Maybe a fairer, more fair way of expressing this. They are not very intuitive. Not very intuitive, I would say. And yeah, about multi-producer single consumer channels, yes, they are a higher level synchronization primitive, like the channels themselves. I think that they are better than atomics if they can be used. You know, if you have a problem suited for channels, it's nice to have this thing on the standard library. Like, they are called multiple producer single consumer. So whenever you're thinking about, okay, I have these multiple things doing things in parallel. Maybe, I don't know, whatever expensive computation, you're doing parallel processing of images or like scraping the web or whatever, and you have these multiple producers of values, and then you want to integrate those results together and into a single consumer. Well, using channels might be a very good fit for that. I think they are easier to reason about than atomics in terms of like synchronization or ordering rules. Basically, they don't have ordering rules. They have different rules for synchronization. You have to think about sending messages and receiving messages, which I think, at least to my brain, is much easier to reason about. But again, they are still a bit boilerplate-ish for common tasks like data parallelism. That is what we wanted to do in this problem. And by the way, there is much more on the standard library, on the standard sync module. There is, things like atomic ref counting references called arc, mutexes, read-write logs, things that can be initialized once, whatever. Like all very useful things and very useful building blocks for doing concurrent work. So yeah, the standard library is great, I think. But then we have Rayon and outside the standard library, and I think specifically for this task of running things like in parallel and data parallelism, it's very easy to do, very intuitive API, like awesome API, very well designed. And yeah, especially the parallel iterators are so powerful and so easy to use that if I have a problem where it's like an iterator problem or something that I'm iterating with, and I say, okay, I could parallelize this, I would go directly to Rayon without even thinking about the standard library, I think, because it's such a good library. I would totally use it again, and I think I will be using it for maybe parallelizing some of my solutions on Advent of Code, maybe in future videos. But anyway, I think that's it for this video. It will be a long one, but I hope you enjoyed this exploration of the different concurrency and parallelization primitives in Rust and also Rayon. And if you haven't, thanks for watching and see you later. Bye bye.